Assalamu alaikum wa rahmatullahi wa barakatuh. Inshallah, today we will proceed what we started yesterday regarding modeling by SEG Software. Yesterday we discussed how to use the different techniques in SEG Software to create parts, how to make gaps, shift to change the center line of the assembly, how to flip the direction of the assembly. We discuss how to make unreal elements, to use it to make childs to another childs. Different points we discussed them yesterday, and today, inshallah, we will complete what we start. But today we will discuss the storage tanks in detail, inshallah. Inshallah, we will make a new project. From here, we will click on New to start our new project. And from here, let's select the location for the project. And now you will be able to select the suitable module. When you select storage tank from modules and click on Create or Finish project creation, automatically, as mentioned, you will get a folder on the location of the project. This folder includes the project files, the SEG file, which is include the data of this project, the inventor IBJ project, folder for parts, folder for assemblies, and folder for drawings. Now let's start with the defining the equipment information. Here, when we select the storage tank with fixed roof, automatically the position of this equipment changed to vertical, and the assembly direction changed from bottom to top. That means you will start from the bottom parts like annular plate or the bottom plates of that shell plates up to the roof. That's the direction of the assembly. Here, as discussed yesterday, they delivered the plate dimensions, and those values are very important to calculate the number of plates for shell and the arrangement of plates in bottom and roof. Okay. Inshallah, we will now discuss the options of filling the design data of this equipment. Here, when you select the equipment, you will get this list, okay, which include some information about the design data of this equipment, like the construction code, internal design pressure, internal design temperature, and more. Now, if you would like to modify those data, there are different ways. The first one, which is double-clicking on the cell itself and modify the value, okay, like that. Okay. And you can modify the values, units, all of that. And if you would like to make this row active, that means when you export the design data to an Excel sheet or to your drawings, this row will appear on the exported data. So from here, if you would like to remove it, just remove the checkbox to remove this row from data exporting. Okay. And if you would like to remove them all, just from select all and remove this checkbox again, all checkboxes will be removed. Now you can select the required fields only. After that, click on Save. Now those data can be modified and edited from this form directly. One more way you can do by adding a new row. If you click on Add Row, you can you have the ability to add another row like area. Okay. And unit. You should fill all data. So you can write here slash or backslash dash or something like that. Instead of keeping it empty, you should have a value. So after clicking on Save, it will appear at the bottom here. So you can add more data plus the current data. There is another way to fill this design data by creating a new Excel sheet. So the design team can do that by making an Excel sheet like design data. And here you will deal with 3 columns. So you should fill 3 columns and no empty cells. So from here, value of the construction code API. Okay, and the second cell or a third cell, we should fill it with any value. So we can write a dash like that. And the second one, which is internal pressure. Okay. And the value will be R, like that, internal temperature. Can be 120. And for the Celsius, to make the degree mark here after the Celsius, you can figure that from here you can detect that it looks like in AutoCAD. To make the degree, you will need to write it in percentage after that D as a small character. So you will get the degree when you export it to the inventor drawing. So from here, let's write it like that. And let's say capacity. Let's say meter cube. So to make a cube, which is to the power 3, from here it's the you can take those characters. It's the same in AutoCAD. So you can take those characters and add them after meter cube to get meter cube. Now, when you click on save, be sure that you fill 3 columns and no empty cells. You should be sure from that, no empty cells. Now let's save this Excel sheet. Now you can import the Excel sheet from here, and let's go to the project folder, which is day 6, and let's select design data. When you click on open, now SEG will ask you if you would like to empty the previous grid or add to it. So let's remove the previous. So yes, you can figure that you get the stored or the imported data from the Excel sheet. Now let's click on save to save those information for the design. Okay, so that's the first way to change the last way to change the design data. So let's revise them again. The first one, by double clicking on the cell itself and change the values. Second way to add your rows, from add new row and fill the data. The third way to import it from an exported Excel sheet or the design team an Excel sheet like that, and the Manhole who will make the modeling can import it directly. Here for the export to Excel, you can export this sheet to an Excel format. So from here, if you click on export to Excel, you can export this file in XLS format with the entire data. Okay, now let's check other thing regarding the app setting. Here for the app setting, as mentioned on the previous session, the options of preview, which is give you the ability to make a rendering for or presentation for element during creation. You can control it from here. Here the style of icons, you can make them mixed icons. So the first icon will be in as a large icon, the other icons will be small. Or if you would like to make all icons in the element tab in large icons, or all of them in small icons. Here that's option for the zooming, and we will discuss it during the session inshallah, which is give you the ability to make zoom extend automatically after importing new items. If you would like to stop it, you can select normal, so zoom extend will stop. Here are some other options for the bill of material. If you would like to make a grouping, if you have more than one equipment. Here the style of nozzle size, if you would like to make it in NBS or DIN, or make it mixed, so like here NBS and between brackets DIN, or you can change it or select the suitable format for the nozzle size. Here for the dimensions in bill of material, if you would like to make it in millimeter or inches, or make it mixed millimeter and inches, that will appear on the bill of material. So in case of inches, you may need to make it in fraction, okay, not in decimal. And in case of fraction, you will need to make it select the fraction of the units. Okay, so let's make it decimal again and keep those data like that. And here the way of numbering. The difference between SEG numbering and sort numbering. The sort numbering will sort the items like 1, 2, 3, 4 up to the end. But in SEG numbering, this type of formatting of numbering will group the items based on the product format. For example, if you have a formed head, the formed heads in SEG database takes a group number 1. So any formed head will take group number 1. So if you have, for example, if you have 3 formed heads in your vessel, head at right and another at the left and one on a boot, for example, so it will take 1.1, 1.2, 1.3. After that, if you have shell courses, it will be 2.1, 2.2, 2.3. So the SEG numbering will be in that way, and sort numbering start from 1, 2, 3, like that. Now let's save the changes, and let's now check the first item in storage tank that we will deal with it, which is the annular plates. Here for the storage tanks, inshallah, we will discuss how to make the annular plates, roof plates, bottom plates, how to create spiral stairs, clean outdoors, and manways. And for the annular plates, we will find 3 different types, and we will discuss, inshallah, in detail. Now from elements, let's open the API elements, and from here, let's select annular plate. Here, for the annular plate, you will find here 3 different types of the annular plate. The first one is equal annular plates. That means all plates will be equal in dimension, the same thickness, the same arc length. All dimensions are the same. So let's check that one. From here, let's define the tank inside diameter. It's 4 meters, for example. And the shell thickness, let's make it 6 meters. That's the first course, the bottom course on the shell. And here the annular plate thickness. So the annular plate thickness, let's make it 8 millimeters. And the projection outside the shell. That means here, let's make that sketch here. That's the shell, okay? And here that's the inside diameter of the shell. That's the inside diameter. And here the thickness. So the annular plate projection, it's the value from the outside diameter. So it will be from here, there, from the outside surface of the shell up to the end of the annular plate. Okay, so here that's the projection of the annular plate. Let's make it 60 millimeters, for example. And here the edge length, which is dimension W. If you take a look to the image on the right hand side, the W parameter value is the edge length of the plate. So let's make it 750, for example. And here you can define the material as discussed on the previous session. You can write it directly or open the material database from here. And that option for straight ends, which is like that image, you can make the end edge as a straight image. So if we take an image like that, flip screen from this one and make from here. So you can make this end with a fillet like that. So it will be like the outside diameter. Okay, or you can make straight. So the option of straight, you can activate it from straight end, which is the checkbox. Now, the bottom thickness, which is will be welded to the annular plate, you can define the thickness of the bottom from here. And from here, you can define the longitudinal welding line orientation for the first plate. Let's make it at 0. And from here, let's define the number of segments for the annular plates. Let's make them fixed. And now let's click on save. Okay, now let's start the assembly to the elements on Autodesk Inventor. And here, because we select parent preview and the child preview options from the app setting, you can figure that rendering or a presentation for element during creation and assembly takes place in Autodesk Inventor. If not selected, it will be run in behind. After that, you will find it assembled on the final assembly. Now we have the annular blades, and you can figure from the quick view, they are similar, no different in lengths. And now let's make one more option for the nesting, how to make a nesting for this part and calculate the required number of blades actually in. Now, after opening this part again, so let's close the assembly. Here from the tree, you have the annular blade assembly. Right-click on this assembly and open it. So you will open it in another window. Now, if you select the assembly from here and create nest, and from here, you will be able to select the units of nesting study. So let's select millimeter nest and click in OK. Now, in that case, the nesting tool of Autodesk will start detecting the material and thickness, okay, to group the parts. So if you have more than one material and different thicknesses, automatically the nesting tool will calculate that and detect the number of groups that you will need. Here, after importing those items, the nesting application detects that you have one material, which is a 516 grade 70, and the thickness of this material is 8 millimeters. So let's accept that, and now the application will extract the parts to get the flat pattern for it. Now it's done. Let's click on OK, and now you can figure the blades will appear on the drawing area. It's now ready to make a nesting study. Before the nesting study, from process material library, if we open the materials, here you will find the default material. That's a default material which is generic. We will not use it, but here from ID number 2, you will find the material that you have. So from here you have that's the material name, and here below the thickness of this material, here the density. So let's change this material ID to be equal that one, and let's make the thickness as 8 millimeters and click on OK. That's just a renaming for the package ID, for the material ID. Here, if you click on package, you can define the length and width of delivered blade that you will use it to make the nesting. For example, here let's define the length as 12 meters and the width as, let's say, 2.4 meters, like that, and click on OK. Now we define the blade dimensions that we have on the workshop to start the nesting. Now from here, if you click on create, you will find some options for nesting, like if you would like to make the start alignment from the lower point and left, or lower point and right, upper point left or upper point right. Let's select lower point left, and from here the alignment of blade, if you would like to make it aligned to the short edge or make it aligned to the long edge, that depends on what you would like to keep. If you have another project, for example, if you have something like that and you would like to keep the long length to use it on another project, if you have, let's say, small blades like that, so you can arrange it in the long or short. So from here, let's make it length and width and start creating the nesting process. Now, in seconds, you will get the result like that. So here, you can figure that after making the nesting process, the nesting efficiency will be 27.5 around 28% from the plate that you will use. You will have 6 parts of plates, and here that's the material ID. It's the material name and thickness, and here you will need 1 sheet, and the arrangement will be like that. So you will need 6 meters point 700, around that, 700 millimeters, and you will need from the width about 1.8 meter, and the other area will be free. Now let's change the blade dimensions. So let's come back again to the package and change the available blade dimensions to 1 meter point 5 and 6 meters length. And now let's re-study again this nesting. So from here, let's start nesting again to check the the editing here in that one. Now you can figure that after making the nesting efficiency will increase a little bit, and here you have 2 plates, and that plate will include 3 parts, and the second plate will include 3 parts. And here, if you would like to export the sheet as DXF, automatically from here you can export and select the extension of exporting to the DXF extension. Now you can figure that you have inside this sheet you will have 3 parts, okay, which is annular plate part 1, part 2, like that. So you have the naming of plates inside each sheet. Now let's close this one, and now let's check another type of the annular plate. From here, from edit, let's reset the inventor model, and now let's select another annular plate type. From here, the second type is annular plate from different pieces. It looks like the shell from different pieces. That type gives you the ability to define the arc length of each annular plate. So from here, let's define the annular plate outside diameter, make it 4 meters, and the annular plate thickness, let's make it 8 millimeters, and the edge length, let's make it 600, and let's make it straight end with a straight end. And here, the bottom thickness of the tank, let's make it 6, and the number of segments, let's make them 6. And from here, let's define the first one length, the second one, and let's update that. From here, let's change this one, that, and click on update. Now we have those plates like that, and let's click on save. Now when we click on start assembly, you will get the annular plates in different dimensions as selected in SEG importing form. It will be like that. So they are differ. Now let's make the same thing, which is nesting. If you open the assembly and from here click on create nest and select nesting to be in millimeter, you can figure that the nesting tool detects the material and thickness, and now the extracting parts process will take place. After that, click on OK, and from material properties, let's change the material name first. So from here, name the material thickness as 8 millimeters, and click on OK. And from package, let's change the length and width, and click on OK. Now let's create the study and keep everything as it is, and let's run that one. Now you can figure that you have the arrangement of annular plates inside this sheet by that way. Okay. So by using the nesting tool from Autodesk and by creating those parts by using SEG, you can figure that in seconds or minutes you can make a study for the nesting for those plates, and that will give you a very powerful option to study your cases in a short time. Now let's check another type for the annular plates from SEG. Let's reset the inventor model from edit. Let's reset inventor model. And from here, let's check the last type for the annular plates, which is annular plate with different pieces and thicknesses. Here with that one, it will give you the ability to define the thickness for each annular plate, plus the arc length. It looks like the shell from different pieces and thicknesses. So let's check that from here. Let's define the annular plate outside diameter, the annular plate thickness, main thickness, and the edge length. And from here, the bottom thickness, number of segments, and let's define that to be that 8, and let's be defining the other bits. And click on update. We need to change the thicknesses here. So the first plate will be 10 millimeters. The second one will be 16. That will be 10. Let's make it 12 and 10. Now we change the thicknesses of plate, and from start angle, when you change the start angle and click on update, you can figure that the other angles will be changed. The same things that we discussed yesterday for the shell plate. If we check that here, based on the thickness, based on the start angle and the length, the arc length of this plate, based on both of those, the end angle will be calculated automatically, and the end angle of this part will be the start angle for the next part. And based on the that angle and the length, we will get the value of the end angle of the second part, and automatically it will be used as the start angle of the next part. This loop up to the end here, it will be the same. Now let's create this part. So from simply, let's click on start to create starting the this type of annular plate. Okay, one more thing here, I missed it. Here I define the annular plate main thickness as 8 millimeters, but all plates here more than 8 millimeters. So we need to keep the current plates here with 8 millimeters. So let's change 10 millimeters to 8 like that, and click on save and upgrade. And now let's start the assembly again to modify the annular plates. And now you can figure that the plates with different thickness will take a different color. That means this plate with a higher thickness than the origin plate on this assembly of the annular plate. Here, after updating the 3D model, you can figure that the thickness of this annular plate is different. So from inspect tool, you can figure that it's 16 millimeters, and for the second one, it's 12. So here, this one is 12, and the main blade thickness is 8 millimeters. Okay, it's 8. Okay, now if we try to make a nesting for this one, let's open it. And from the annular plates, let's make a nesting by create a nest study, and from here select millimeter. So during this process, you can figure that if we take a print screen here, and here you can figure that the nesting tool of Autodesk detect that you have 3 different groups here. Let's minimize this thickness, give it a red color. Now you have 3 different groups. The first one with all of them with the same material, but with different thicknesses. You have 12, 16, and 8 millimeters the thickness. So this tool is smart and automatically will make things easy for you by making grouping for the identical materials and thicknesses. Now let's come back to Autodesk Inventor and click on Save. Now the extracting data is done. Click on OK, and now to define the first material, which is material ID 2 with 16 millimeters. So let's take this and rename that one. 16 meters. Okay, and the second one with 8 millimeters. The third one with 12 millimeters. So rename. And click on OK. Now you can define the package length. So from here you can change the dimensions of the annular, the available blades in your stock, and from create and click on OK. You will get 3 different groups. So you have one or a single blade with 16 millimeters. So you will get it like that, and you have 4 plates with 8 millimeters thickness. Here, that's the material with 8 millimeters. So they will be arranged like that, and a single blade with 12 millimeters thickness, and it will be arranged like that. And here you will find the nesting efficiency per each blade and the number of parts inside this sheet. Now let's close this and let's check another part inside SEG application. So from here, let's from edit, let's reset inventor model, and now we will discuss. Let's delete this part and let's discuss the available types for the bottom. First, we have the radial bottom or radial roof. After that, we will discuss the different types of flat bottom as arranged blades, and flat bottom with inside slope or outside slope, or with slope from one side, which we discussed the fill type yesterday, which is tilted from one side at the bottom to suit this type of tanks. Okay, so from here, let's select the vessel node or the equipment node, and from elements, let's select radial roof. Okay, so from here, let's make it as bottom. Okay, and click on add. And when you select it, you will get the form of this part. And on the right hand side, you can figure that you can use this part as a radial roof or radial bottom. To make it radial bottom, you will need to activate this checkbox, this bottom. Okay, so if you don't select it, it will be a roof. If you select it, it will be used as a bottom plate. Now you can define the inner diameter of that radial plate. From here, the thickness. Let's make it, let's say 6 millimeters. The start angle, let's make it at 0. The sloped angle, let's make it 1 to 25. The gap, you have a gap, the inner diameter, 4 meters, and the number of segments, let's make them 8. And here one more option, which is the lab activation. If you would like to make a gap lab between plates, you can select this checkbox. If you would like to make a gap, just find the gap value from here. Okay, so it's the weld gap. But if you would like to make an overlap, just select this checkbox and define the overlap between plates. Now, when you click on Save and click on Start Assembly, you will get the blades of the annular blades of the radial blades of the bottom of this tank. And you can figure that you have a lab between parts here and there. Okay, after creating that, if you take a look from the top view, you can figure that you have a lab between elements with 15 millimeters as defined. Now, let's make the same thing by making a nesting for that. If we open it like that and try to make a nesting, so from here, create nest, create nest study. Okay, and now the application detect the thickness and material, start extracting files. And now let's click on OK. Now, if you start defining this material or click on create directly to start make a nesting, you will get a nesting for the bottom plates like that, and you can figure that how much time you can save in case of making that by using the SEG software and the nesting tool of Autodesk to make a quick study for the blades and the required plates to start your fabrication. Or to start your procurement process, because you will need to calculate the actual plates that you will need it in fabrication. Now let's check another part of bottom plates. So from edit, let's click on restore inventor model, and now let's delete this part and let's use another part from elements and API elements. And now let's check the flat bottom, arranged flat bottom. Okay, so from here, let's make it bottom. And now you can figure that this, if you take a look to the image on the right-hand side, the bottom here is parallel to the ground, and the ground is in a horizontal level. No tilted angles, it's just horizontal. And from here, you can define the bottom plate thickness. Let's make it 8 millimeters. You can define the overlap, define the inside diameter of this tank, at 6 meters, for example, and the torch cut tolerance. Here for the torch cut tolerance, if let's make a new image, and actually, if you have a blade like that with, let's say, 6 meters length, and here that's the height, and like that. And if you use a torch to make a cut on this blade, to divide it to 2 pieces or more than 1 piece, in that case, the torch cut has a tolerance. So you will lose an area here at this blade. So if you cut it in 2 pieces, 2 equal pieces, and let's say the cut clearance, let's say it's 50 millimeters. It will not reach that value, but to explain what I would like to say. So the torch tolerance cut, let's say it's 50 millimeters. So you will get a length here equal. So from here, it will be 6 meters minus 50 millimeters. So you will have this value. It will be divided by 2. So the length of this plate, it will not be 3 meters. It will be like that, 2975. So that's the length of this piece. So SEG will use the torch cut tolerance to calculate the half piece actual length. Okay. So it will be in that value, not in 3 millimeters. So if you would like to use it as a 3 meters, would like to use it as a 3 meters, So from torsion tolerance, you can make it as 0. Okay, so 0 here will make the half plate equals the half delivered plate dimension. I hope this point becomes clear after making this case. So again, if you have a cut on a plate, you will lose some area here based on the torsion cut tolerance in this area. So the half of the plate will not equal the half value of the origin plate length. It will be less than that. To avoid that, if you would like to make it equal the accurate half length, you can define the torsion cut tolerance in 0. Now, if you let's save this and let's open the update table, you can figure that the scale of this circle is a little bit small. So if you would like to increase it, just increase that scale. It depends on the resolution of your screen. So from here, if you click on save and open the update, you can figure that with the scale now a little bit changed. Now, to check some options regarding the arrangement of plates, here, if you make, you will find here at the top the some options for the plates as not the origin plate on the row. Let's check that first to indicate this point here. If you create the draw or make a draw plate, you can figure that you have an orange or let's say not orange, orange plate here and a white plate here. It will be appear if we change the size of this bottom. Let's increase it a little bit, make it like that, 20 millimeters. Okay, and let's increase the scale a little bit. And here, if you make a draw, you can figure that you have a brown or orange plate here. In each row, you will find this plate with that color, and that's the reference plate in each row. So if you would like to change the orientation of this plate, make it on a line to left or right, or make it offset, change the property of the origin plate, you will deal with it from here, from the origin plate setting. So let's take the screen. From here, look at that. You will find here that place, which is the origin plate setting. So you can make it as a full size, half size. You can make it with offset. You can define the width of this one. Okay. And the other plates on the same row, you can deal with it from here. Okay, sorry, from here. So you can change the other plate thickness from the width and height. Those options on those check boxes, those options give you the ability to create the first arrangement, and we will discuss each one of those in detail, inshallah. Okay, let's come back to the plates here. So from this 4, if you select this plate, for example, you can change the size of this one. This one is a full plate length. If you select it, you can find here from the information here for the information tab. This tab, the information of this plate, like width, height, and it's active or not, and the arrangement of this plate and the number of this plate on the SEG file. So from here, if you select this one, you can change the size of this one to make it as a half plate. Okay, so you can change this one to a half plate, or you can define the width of this one. Let's make it, let's say 3 meters, for example, and click define. So you can control the size of this one. Okay, you can make it aligned to right or left center. So if you make it right, it will be on the right side, and you can make it on left. So you can change the position of this one. You can make it centered and change the width of this one and change the offset. So for example, if you would like to change the offset of this one like that, so you can move the start line of this one from here, and you can, if you would like to divide it and split it from left, you can make that by that way and change the length of this one. like that, and make it near to the first weld line. And we will discuss the options of that in detail. But right now we would like to define the main types of the bottom plates and check the configuration of each one and how we can deal with it. Now let's modify this piece again. Let's reset the inventor model and come back again here and make this one as 6 meters. And from here, let's click on save and update the blades. And let's check the options here for the mid row and reverse. For the mid row, for example, if you select this one and click on update, you can figure that you will have a mid row in this in the arrangement. Let's increase that. Okay. If we select the mid row and make it like that, so here if you take an image and look here, you can figure that if you make the center line of the vessel, you will get this line and line vertically. So you have here a row on the middle. You have a row here on the middle of the arrangement. Okay, so if you would like to start your arrangement from top to bottom, you can make it like that. So let's remove this checkbox and reset the grid again and make draw blades. So the arrangement will start from top to bottom like that. And you will have a weld line at the middle instead of a row at the middle. Okay, so if we take an image like that and create a new image, and you can figure that the weld line will be at the middle like that. So if we open this one, you can figure that you have a difference. Here you have a mid blade, but that one you have a weld line at the middle. Okay, so this option gives you the ability to create a mid row on that bottom or roof. Those options will be applied on roof or bottom. Now let's reset this grid to remove the arrangement. And now if we make mid row and draw plates, you can figure that you start with a blade here and a complete plate on the middle. Now if you would like to reverse this arrangement, make 2 blades at the top instead of 1 plate. So let's reset grid and make it reversed. Okay, and let's draw plates. You can figure that instead of 1 plate at the top, you can reverse that, and instead of 1 plate at the middle, you can make it half plates, and here you have a complete plate instead of 2 plates. So you can reverse the location of welding lines. So those options give you the ability to make a startup for the blade arrangement. Now let's remove those options and remove the reverse and check another option, which is all centered. Okay, so all centered will give you the ability to make all blades on the center. If we take an image like that and new image, here you can figure that all blades will be on the center. Half of this plate on the center, so the center go across the half of each plate. So if we increase the size of this plate a little bit, so let's make it, for example, 5 meters, and select mid row and all centered and click on draw plates, you can figure that all plates now centered with the center line of the vessel. So all plate will be like that. You have a full plate and the mid plate, full plate and the mid plate, like that. So the arrangement will be in that way. So if you would like to flip the direction, so let's reset this one and select flip and click draw. So you will flip the direction. It's the same like reverse, but with all center. So you will have a complete plate, half plate, complete plate, half plate. So let's check it again by removing this and click on draw. Half plate, complete plate, half plate, complete plate, like that. So you can make the arrangement in that way. So those are the options of start creating the arrangement. Inshallah, we will discuss the those options in detail, how to change the dimension of blades change the orientation. But now let's discuss that if we have, let's say, this tank diameter and make it update plates. And now let's add a mid plate row plates. Now we have those 4 plates and make the start longitudinal welding line orientation at 0. And now let's save that and let's create the assembly. Now we have the bottom plate arrangement. As you can figure that we have an overlap here. Okay, so the distance from here to there is 50 millimeters, which is the overlap that we defined in the form. Okay, it's 50 millimeters appear here and there. Okay, now if you would like to make a nesting for that, by the same way, if you open the assembly and create a new nest, select the nesting study. Now you can figure that the material is appear here and the thickness, they are the same, with the same thickness. After that, let's create a nest and click on OK. One of them is greater than the available plate dimensions, so we need to increase the width a little bit. So from process here, let's change one like that and click OK. Now we have the plate arrangement like that. So you can figure that you can define the plate length, width, and dimensions based on the available plates in your stock. So you can change the value based on the actual values in your market. So here you can detect that those plates need a larger values, so you can automatically come back to SEG and change the plate arrangement and define the suitable arrangement for this plate to get an accurate nesting for this one. Now let's check another type of bottom plates. So from here, from SEG, let's click on Reset Inventor Model, and let's delete this part and create a new part from elements. And from API elements, let's select the arranged sloped bottom. Okay. Inside this type of bottom, you will find 3 subtypes. The first one, which is sloped bottom to inside, like that. So you can make a sump at the middle, like that. So the flow will goes to inside, and the sloped to outside. So the lower point will be as the edge of the tank, like that. So you can make the sump at the end, not to the center. Another one, which is sloped bottom from one side, which we discuss the shell type for that one. Okay. Open a new image like that. Yesterday we discussed the type of making a shell which suits this type of tanks. The shell has a short edge and long edge from one side. So from here, by using the sloped from one side, the bottom, you can make a ranged flat bottom sloped from one side. Now let's check the first part, which is sloped from to inside. You can define the bottom plate thickness, the overlap between plates. Here's the inside diameter and the sloped length. Let's make it 1 to 50, for example, and from here the torch cut tolerance. Change the scale and click save. Now if you open that plate, you can draw the plates by that way, and the same steps you can generate the 3D model of this part. The difference here for the sloped bottom to inside or outside, it's not in one plan. Okay, here if we take a look here for the flat bottom plates, all plates located in one plan. So the arrangement of plates, you can get the sheet metal development. Sorry. You can get the sheet metal development for each piece directly from the assembly, because all the assembly located on one level. But in the sloped to inside or sloped to outside, actually you have a diameter greater than the actual length. Let's check that here. If you, for example, if you let's create a new paint drawing here with, let's make the slope a little bit big to define that. And here that's the bottom. It looks like the same thing will be for the roof. Here you have the inside diameter of the tank, and here the sloped value. Let's make it 1 to 2 to make here the slope will be not 1 to 100 or 1 to 50. Let's make it 1 to 2 or 3 to check that the outside diameter here, this bottom, not equals the actual one. Here you have this edge, so that's the radius of the bottom, not that one. Okay, so here that's not the actual value of the tank. I hope here if we take a look at this here, if we make this slope 1, let's make 1 to 2 and click on save. Now the inside diameter, the bottom plate diameter, now actually it's not 8 meters. If you open update plates here and take a look to the part at the top here, the actual diameter which used in calculation, it will be around 9 meters, not 8 meters. Because the slope on the tank, the actual radius here, if we make the slope like that, so the radius that you have now will be that value, which is the aligned length, not the perpendicular length to the center of the tank. Okay, so the value, the actual value here of the inside diameter will be greater than the radius of the tank. Okay, so the calculated value for the diameter will be changed. So SEG will use this value to calculate the arrangement of plates like that. So you will get a value or a sketch like that, and the circle diameter will be with that value. So let's decrease it a little bit and click on save. Now click on update. You can figure that the diameter here now changed. If we take a print screen and from here, let's open another one and make paste. Now you can figure that based on a slope, the diameter of the actual diameter of calculation now change it. Here we have that value, and here we have that value. And if you take a look to one of the others, okay, that's for flat. It was the same inside diameter of the tank. It's the same inside diameter of the tank, but here it's by using the actual length of the of this sloped line, the diameter of this bottom will be calculated by that way. Now, if you click to make plate like that, you will get the diameter by that way. Okay, so that's the difference between the flat and sloped to the bottom. Now let's increase this one a little bit. Let's make it 1 to 50 or 1 to 20 and click on save. Now again, if you open that one, the value will be decreased. Let's draw the plates like that and create change. the longitudinal welding line orientation. Click on Save. Now when you click on Start Assembly, you will figure that those plates takes a tilted angle to the bottom. Let's take a look from here. You can figure that it's not straight at the bottom. It takes a tilted angle based on the value of slope that you define. Now to get the flat pattern of this part, it not looks like the previous one for the flat bottom. For the roof and bottom with a tilted value like that, you will need to get the flat pattern from here. From this form, you will get some actions here. One of them is create flat bottom, okay, because this assembly is approached assembly, not from blade. So if you open those parts, you will not be able to get a shell development for it because it's formed on not like a sheet metal. So you will need to create the sheet metal for this one. So by clicking on create, now you will create the sheet metal development for each part. And if we put it on a drawing, you will figure that the outside diameter of this one will be like that value, which is at the top here, will be like that value. Okay, and if you take a look here, you will get a slice cut here, which will give you the value. But here it's because of this sloped angle is small, so the cut value could be neglected. So to make this value appear clearly, let's come back again here and let's reset the inventor model and increase this value again to make it 1 2, and from here you can figure that the diameter increased, and if you make a draw, you will get this arrangement. Now let's change this value and save it. Now if you click on assembly, you will get the bottom plate assembly, and you can figure that it's clearly appears that the cone slope or the bottom slope is visible, clearly visible. So to get the plate arrangement for this cone, here you have this bottom, it's like that. So to get the flat pattern for that, if you measure, by the way, if we add this part to a drawing and put it on a drawing like that and measure the diameter of this one. So let's measure the diameter, so to make it with a radius. So from here, let's select the diameter. So the diameter is 8 millimeters. Okay, and you can figure that the arrangement is okay. But here to get the sheet metal development of this part, you will need to create the flat pattern. So let's create the flat pattern for this one, and I will show you the difference between the original flat pattern and the approached 3D model for the blade arrangement to get it on the 3D model. Here, that's the slice. It will be calculated and located on the right place. And now, if we come back to the drawing and open this drawing, and let's add the origin flat pattern for this bottom and click on OK. Now, if we measure the diameter of this one, let's add the diameter instead of radius. So you can figure that the diameter here is the actual diameter, which is, as mentioned here, which is double the actual aligned value for that line, which is that value. Okay, which is that value here. Okay, so that's the actual diameter of the blade after getting the flat pattern. If we come back here to the 3D model, because of you have a huge value between the slope 1 to 2, so you can figure that that's the slice angle that you will need to remove it to weld this edge with that edge to get the conical shape. Now, to get the conical shape, you will need to cut a slice. After that, you will need to weld that edge with that edge. So here, that's the, if we make this color with a shaded color, the black area here, that's the slice cut that you will need to cut it. After that, you will need to weld this edge with that edge to get the conical shape and get the final shape of this one. So that's the flat pattern arrangement for the bottom, and that's the approach at the 3D to make it appear on the 3D model of the tank. Okay, I hope this point be clear. And before going to the next step, if you have any questions regarding to this point, which is the actual diameter and the slope, kindly share it with me to answer you if you have any questions. Okay, no questions in this step. So let's complete. Okay, so from here, let's check another type of slope. Bottom. Let's reset the inventor model. And from here, the same thing with the sloped bottom to outside. So the highest point will be on the middle. It's the same options that we discussed in the sloped bottom inside and outside. The same option, so no need to repeat it again. For the sloped bottom, from one side, you will figure that it's a little bit different from the two previous parts. And here, one more point here, this bottom located on one plane. So the diameter of that one will be okay. Not looks like the slope to inside or outside, because as mentioned, it's located in one plane. Now, not a conical shape. It's in one plane. Now, let's define the bottom plate dimensions. It's 8 millimeters. Here's the overlap and the bottom plate diameter. Like that. That's the slope. Let's make it to 10, and the torch cut tolerance, and the cut orientation. Let's make it 90 degree, and tank diameter here, and the tank first course thickness. And let's click on save. Now, if you open the update tab and pro blades, we will get that shape, change the orientation, and save it. Now, if you create this part, here those parts will be assembled, and it will be assembled with the final model of the equipment. So here it's the sub-assembly of the bottom, and now it's assembled to the final assembly of the equipment. Now, if you would like to make a nesting for it, you can make a nesting directly, because as mentioned, we take a look from the back side, it's located on one plane. Okay, so easily you can get a flat pattern development for this one. So you can create a nest for this one directly from here. No need to create a sheet metal development or create a flat pattern for this bottom. Now we discuss the types of bottom in SEG. We discuss the radial bottom, discuss the flat bottom, sloped to outside, sloped to inside, and sloped in one side. Now let's discuss the roof options. And from here we have we discussed yesterday the shell type options. And now let's discuss the roof types and roof options, and in the next step the compression ring. Now for the roof, let's delete this part, and from the assembly, let's come back here. So in this list, we discussed the annular plates, the radial roof and the bottom. They are the same. These are just a checkbox to differ between them. And we discussed the flat bottom and arranged bottom. This type includes sub-3 types, as mentioned, which is slope to inside, slope to outside, and slope in one side. Now we have some different options for the roofs. One of them is radial dome roof. Okay, so you have to define the inside diameter of curvature of the dome roof, arranged flat bottom roof, and arranged roof from plates, arranged dome roof, and aluminum dome roof. Now let's start with the radial dome roof. Okay. So from the dome roof, you will need to define the radius of the curvature at the top. So here that's the radius of curvature. Here you can define the opening at the top and the inside diameter of the bottom inside diameter of this roof, the thickness of this roof, and the start longitudinal welding line orientation, and the number of segments. And if you would like to make an overlap between plates, you can make it from here. Or if you would like to define a gap between them, like butt weld, not overlap, so you can remove this checkbox. Now, if you click on, let's make an overlap and click on Save. Now, when you click on Start Simply, you will get the roof plate arrangement. Okay, and after creating the assembly, it will be assembled to the final assembly. And here you have the radial segments of the dome roof here. And by the way, no option to get a flat pattern for the blades, which takes a deformation in two sides like dashed head. But there is an option for unfolding in Autodesk Inventor. You can use it. We discussed it before, which is unwarp. If you select this surface, for example, you will get the unformed dimension of this plate as a surface, so you can get it as a surface, and you can extract the dimensions of this plate. And here the red areas is the most tensioned areas during forming. Okay, but no flat pattern option. It's just unwarp, which will give you the ability to get the surface before forming. Okay, now let's click on OK and do this. So that's the first part of roofs. Let's edit, reset the inventor model, and delete this part. And from here, let's add another type of roofs. So from here, let's add a dome roof as arranged plate. So from dome roof, let's roof. And here, let's define the inside diameter, thickness, the overlap, and the inside diameter. And now if you try to update this model, you can figure that here if you make a print screen for this one. And from here, let's print this. Here, that's the diameter used in calculation. Okay, not the inside diameter of the tank. It's the actual value here. If we imagine that the dome roof, so the arc length from here to there, that's the diameter, which that's the radius which used to calculate the diameter, the actual arc length for this dome. Okay, to get the actual diameter of the plate. Now let's generate the plate arrangement. Let's draw plates like that, and now let's change the longitudinal welding line orientation and save. And that type, actually, you can get a flat pattern for it. So from create flat pattern, you can get the flat pattern, not the deformed configuration. Now it's on a plan, so those plates are on plan before forming. And here the slice cut. Okay, here's that the slice cut that you will need to remove it from this roof to make it as a dome roof. Okay, now let's go to another type of roofs. From edit, let's reset the inventor model. Let's remove this type and let's add another type of roof. Now we checked the radial roof, dome roof as a radial, and dome roof as blades. Now we need to discuss two more types, which is arranged blades roof from arranged blades and aluminum dome roof. Let's discuss this type first. Here, let's add roof. Here, it's the same option, so you can define the roof top hole and thickness, the slope, the overlap, the bottom inside diameter, material, torsion cut tolerance, and after that you can make update for dates. So it will be like that, and from here you can export and create the flat pattern by the same way to get the flat pattern of this one. And you can figure that here when we define the inside diameter, it's 25, but the calculated inside diameter here is a little bit more. Okay. We make this here, and here it's greater than 25 millimeters. That's because, as mentioned, the slope of this roof. Okay, now let's go to the final type of roof. Simply, let's reset inventor model, delete this node, and let's create the last type of roof, which is aluminum dome roof. And for the aluminum dome roof, you will find two different types, which is include a hexagon at the center. You take a look to the image on the right hand side. Here that you have a hexagon at the middle, this hexagon, like that, or you have a pentagonal shape. So you have 5 edges instead of 6. So let's open this one. From here, you will find here you have 5 edges at the middle, which indicate the center of this aluminum dome roof. Now to define this one, let's define the radius, K, which is a curvature of this aluminum dome roof, and the thickness, the end diameter, which is the tank diameter, or the diameter of this piece, which will be located on the compression ring or another configuration. The levels, which is the number of segments along that one. Here, for example, you have 1, 2, 3. So those are 3 levels, okay, on that image. So the levels will give you the ability to control the number of segments along the curvature of this one. So let's make it 10 segments, for example. Here you can define the material of this part, the longitudinal welding line orientation, and the density of this material to calculate the weight of this material. So if you have another material, you can define the density per gram per centimeter cube. So let's click on save, and now let's click on start. Simply start creating this part. it takes a little bit time to calculate the number of segments and to arrange the configuration of this roof. Now it's done and assembly to the final assembly, and you can figure that now you have this roof. And if you would like to change the number of segments, just change it from here. It's up to 10 levels, so you can decrease the number of levels. As discussed, if you take a look from the top view, that's the first. If we go inside this one here, that's the first level, the second, third level, up to, okay, so each rectangle from those defined a level. So that's a level, that's a level, okay. So here, each two of those defined a level as a circle. So you can define the configuration of this roof. Now let's discuss the options of the compression ring. So from here, let's close this one, and from elements, let's open the compression ring. Now we discuss all features here for annular plates, roof, and bottom. And now let's add the compression ring. Therefore, the compression ring, you can define the shape of this compression ring based on the available features in the API. So it's the detail B on the API. It takes this configuration. So you can define the bend diameter, which is the outside diameter of the tank at the top. The tank offset, if we take a print here and come there, the tank offset, which is that value here, that which is the gap from the end of the angle up to the end of the tank. So you can define that height, which is the offset from the tank. Select the standard of this equal angle from based on the Australian codes, European code, ASIC, or Japanese code. So you can select the equal angle standard, and from here you will find a list for the angle, so you can select the suitable size for your case. After that, you will figure that the length, thickness, and radius dimensions of this angle. And if you would like to make it as a user defined, you can define the dimensions of this angle manually, if it's from plate, for example. Hole activation, if you would like to add a hole at the top of this one, so you can make it as a bolted connection, as a flange with a bolted connection. And sometimes, actually, we create this option based on one of our clients. They make the roof blade with a flange at the end, and they make it bolted with the because they have a small diameter tanks, and they are design it to be bolted at the top. So we create this option for them to make the top angle with an option to tight another flange with it, or another blade with a hole. Okay, and you can flip the direction of this angle to make it to bottom instead of that configuration at top, like that. Another type, which is detail C. Okay, to make this type appears clearly, let's delete it and add a shell. From here, let's add can 1 or pipe. So from here, let's make it as a pipe. Okay, like that, no problem. And that is outside diameter. Okay, let's make it millimeter. And let's add a compression ring to this one. So from elements, let's add compression ring at the top of this pipe. Okay, and this compression ring, make it with that type, the inside diameter. Here, the offset from the top, and you can select the standard, the size, and click on save. Now, when you click on start assembly, you will get the compression ring at the top. If we make a section, make a half section here along this part. If you configure that, you make this angle like that. So if you measure the offset from here to there, which is 10 millimeters, that's the gap of the, which is the offset from the tank end, which is that value. And if you would like to activate holes, so from here you can, if we measure the diameter of this angle, the outside diameter, here that's the outside diameter, so we can make the bolt circle diameter like that, and the hole diameter keep it as it is. Okay, the orientation, make it at 0, no problem, and click on save. Now if you click start assembly, now this flange can be holed like that, so you can use it to for tightening. Now the one other option, which is flip angle, to flip the direction of this angle. So the angle will be flipped like that. Okay, so you can use it as another flange for tightening if you have another connected item to this one. Now let's remove those, save this, and let's discuss another type. So from edit, let's reset the inventory item, and from here let's create another type, which is detail C, and in that type you can figure that the angle will be to the inside of this pipe or this tank, not to the outside. The first type the angle will be outside, but here the angle will be welded to the inside of the tank. The same information for bolting, holing, and angle size. Another type, which is detail D, you can figure the face will be to the face. So from here, the bended radius will be the pipe radius. If we come back to the pipe here, so the inside diameter of this one will be that, and twice the thickness. So that's the inside diameter. So if we take the value copy and come here, select type D, and import this value here, and no need for the offset. And right now, if you click on save and click on start, if we take a section, half section, for that, it's edge to edge. It will be welded like that, edge to edge. So that's another type for that detail. Another one, which is detail E. It's edge to edge, but the angle will be to inside, not to outside. So the difference between D and E, the angle comes to outside, and E angle to inside. Detail I, you have a plate here instead of angle, and this plate you have a length for this one, so you can define the inside diameter, thickness, and inclination angle of this plate, the stiffened length of this plate, the total length, thickness, and longitudinal welding line. So let's increase the pipe size a little bit. So let's set the inventory model, and from here, from the pipe, let's increase the pipe size. Let's make it 60 millimeter, and now it's user defined thickness. So we can define the thickness of this one, make it 3 millimeters, and the height meter. And from here, okay, so the outside diameter of the pipe, it's 1,524. Okay, let's select the type I, shell ID, and the shell thickness, the inclination angle, you can define it, and the user defined length, and the total length of this plate, the thickness, longitudinal welding line orientation, and the number of segments. Let's make them 8 and click on save. Now let's minimize this value a little bit and start simply. So if we take an image from that, come here, where that you have parameters for, which is L0, okay, and the total is L0, which is the we defined it as 200, which is this one, LE, sorry. That value, and that's the total is. So we will have 200 millimeters outside the can here, which is LE, and the other length will be like that, so we can get that shape. If we take half section, we can figure that we have this configuration like that. Okay. Here we define the inside diameter as the outside diameter of the shell, so you can figure that we have a gap here. It's not laid on that one because by mistake we define the inside diameter of the shell as the outside diameter of the pipe. Okay, so if we correct this value, so to calculate the inside diameter of the shell, minus 40 millimeters, that should be the inside diameter of the can. So we can modify this value here and click on save. And let's change this value to 100 and keep this like that. And when you click on Start Assembly, the blades configuration and dimensions will be changed based on the inside diameter change and length and width. Now you can figure that it's located on the end of this shell, and here we have 100 millimeter and the total length is 300 millimeters. So this shape for the compression ring type I. Now let's discuss another type, which is detail I, roof plate at top. So here the roof plate will be at the top of this compression ring, and here for select detail I part, the roof plate will be at the bottom, and here the roof plate will be welded edge to edge. Okay, that will be changed as we discussed on the previous session. The location of the user coordinate system that we will use it to assemble the parts with each other. So the difference between those parts which control the location of the next part. For here, for the top, the next part, which is the roof, will be at the top of this compression ring. In that case, the roof will be at the bottom of this compression ring, and butt weld, the roof will be on the same level of this compression ring. So those are the different types of compression rings. And now let's create a sample from scratch to add the spiral stairs, clean outdoor, some manways, and prepare the 3D model of this one. Inshallah, I hope we can start on the drawings today, but if we don't have enough time to make the drawings, inshallah, we will discuss drawings in detail at the last session for pressure vessel. So this session will be could be merged between pressure vessels and tanks. Because we will discuss the drawings, how to prepare the drawing, how to create the bill of material, how to reflect the balloon numbers in drawings, how to make details. So the last session could be merged into the two departments, like the first session, in which we discuss the basics of modeling in 3D modeling in SEG. Okay, now let's start to create a new storage tank, and from elements let's add an annular plate. So from here let's create annular plate, and from the annular plates let's select the first type, define the tank inside diameter. So let's make it, let's say 14 meters. Okay. The first course thickness of the shell, let's make it 12, and the annular plate thickness, let's make it 10 millimeters, and the projection, let's make it 16 millimeters, and the edge length, let's keep it or change it to 800. Change the material, and the bottom thickness shall be 8 millimeters. The longitudinal welding line orientation, let's keep it, make it 0, and make the number of segments as 12 segments. Now let's click on save. Now when you start creating the 3D model, we will get that shape. Now during the creation of this shape, let's calculate the diameter of the bottom plates. Here, if we let's open a new drawing, and from here let's check that we have, that's the tank, and here the side diameter, it's 14 meters, and the thickness of this tank is 12. So the inside diameter, the outside diameter of this tank will be 4. And we have a projection for the annular plate. We have an annular plate here. So the projection here is, I think we defined it as 60. I think. Let's check that. So yes, the projection is 60. And the here the annular plate is generated. And here the length, the total length here of that one is 800. So to calculate the inside diameter of this tank, we need to calculate that one with overlap. We need to make an overlap with 50 millimeters. So from here, we need to calculate that radius. After that, we need to calculate the same radius plus 50 millimeters in each side as overlap with the annular plate. So to calculate that here, so from here, that's the inside diameter plus twice thickness plus twice the annular plate projection. So here we have the outside diameter of the annular plate. Okay, so if we measure this value from here, so from this section, if we measure that value, so that's the diameter here, it will appear here. Okay, 14,144, the same value here. And now let's decrease the width of this, the width of the annular plate. So let's decrease the value, and which is 800 and 800. So that's the inside diameter. So let's take a copy from this and put it here. That, so that's the inside diameter, and let's increase 100 millimeter as 15 millimeter overlap between that one and that one. So from here, let's increase 100 millimeters. So we have this value. So that's the annular plate diameter. Let's add another plate, which is the annular plate. So from elements, let's create a bottom plate. So let's make this plate as a flat bottom. So from annular plate, flat bottom, let's add 8. And from here, let's add the define the bottom plate thickness. It's 8 millimeters. That's the overlap, and the bottom plate diameter. We will put this value, and the torch cut tolerance. Let's make it 0. Increase the scale a little bit. Click save. Now we have defined the bottom plate dimensions. Now the arrangement of the bottom plate. Let's select mid-row and click on draw plates. As you can figure, now you have the default arrangement based on your selection, as you have a mid-row here on the circle. And if you would like to make a modification on this plate, you can make that by changing the length of this one. For example, if you would like to modify or edit this length manually. And by the way, the arrangement here based on the setting which you defined here, which is the plate length and the plate width. So for example, if we change this one to 6 meters and meter point 5. Click save. Now if you come back to the bottom and open the plate, let's save this one like that, and open the bottom plate. Let's decrease the scale a little bit. Okay, and like that, and create a mid row. You can figure that the arrangement, we have the same diameter, but the delivered plate dimensions changed. Now you will get a different configuration for the plate arrangement. Here you can figure you have a mid row, and the plate dimensions is 6 meters and 1.5. So all plates will be calculated as a large plates, and on the edges you will get the remaining plates. Let's pick another option, which is make it all center. So with all center, you will get the arrangement, all origin plates on the center, but you will have half plate, complete plate, half plate, complete plate by that way. And if you would like to reverse that, as discussed, you can select flip and draw to flip the arrangement by that way. I think you have a small plates here, so it's not the good way to do that. So let's reset that and remove the plate, and from here you can change that by that way. Now let's discuss another option regarding the plate splitting. Here, if you would like to split a plate like this, just by selecting it, you can make a split for this plate and select the complete plate from here, which is that one, not the one at the end. So you can select this one and define the width of this one. So let's make it 2 meters and click on update to update the width of this one. So when you select it, automatically you will get the information of this part here. With this one. So during the selection of this plate, and you can make the modification for the plate setting, not the origin plates, because the origin plates you can modify from here. So when you change the width and click on update, you will get the information of this plate here, the height and width and the number of this plate on the arrangement. Now let's come back here and increase the width a little bit. So let's make it 3 meters, for example, and click on update. Now you will change the plate like that. Okay, for the origin plate, if you would like to make it as a half plate, just as discussed, you can make it full size or half size, so you can change the size of this plate. You can make it with an offset. So the offset the first weld line here will be at the middle. After that, it will be offset. So, for example, if you make it with 1 meter offset from the middle, so the edge will be offset from the center line to here. After that, you can make a split for this plate and define the length of this one. If you would like to make it centered again, you can select this plate and make it center, so it will be centered again. You can make it align to right or to left, so you can change the orientation of the plate by that way. Another option here, you can make it by flipping the direction of the plate, make it vertical instead of horizontal, and that will give you the ability to merge some rows. For example, you need to make those rows merged. Before merging, you should convert this row position from horizontal to vertical, and automatically you will get the color of the row as a green. Now you can make a merge between rows. So from here, if you select this one and select merge vertical rows, now you will get a merging between those rows. Now you can, for example, split this plate and define the width of this one. Like that, you will get this plate, and here you can figure that the weld line will be close from this one, so you can increase the origin plate at the bottom. So by selecting it from here, you can define the width. So we can make it, let's say, 5 meters instead of 3. So you can increase it a little bit, so you will get a gap here. And now you can make a split at this one again and define the split Let's from here, let's say 150 again. Update another split here, 108, like that, and you can make a merge between those two cells. So you can merge this cell with the previous cell, make it as one cell again, and the same thing you can do it with the origin plate. But inside the origin plate, you will find another option. Don't use split row, because the split row you will divide this row again to 2 rows. Okay, you will use split right or left. Okay, so you will keep the origin plate at the right side, and if you use split at left, so you will keep the origin plate on the left side, and you can define the value of this origin plate like that, okay, and make it change this plate width that way. Okay. Now you can make the changes on your plate by the bottom plate by using this technique of splitting. Now, after make changes, you can change the first longitudinal welding line orientation. So let's make it with 10 degrees and click on save. Now, when you click on start assembly, you will start creating the bottom plates. You can figure that how much time you can save if you are using the CAD software separately, and here in that case by using SEG software to generate the sketching parts and making the assembly in seconds. Now, after making this bottom, let's create the first shell course. Okay. Now some calculations for the plate dimensions to reflect it on the bill of material. And now it will be assembled to the bottom, the annular plate, and you can figure that the overlap here with the annular plates will appear. Now let's create the tank plates, and from here let's add a shell course, and from elements let's create can1. And from can1, let's make a shell from different pieces and the thickness. So let's select this type and define the inside diameter of the tank. They define the height, and as mentioned, the height here should be the not more than the defined value in delivered blade dimensions. Here the thickness of the can. So let's check what's the value we entered here. It's 12. So let's come back again here and select this type. Define the inside diameter, height, and the thickness. And we have here from the calculator, if we open the calculator and calculate the arc length, total circumference, it will be 44 meters, around 44 meters. So if we divide that the big length again, 44 divided by big length, at least we need 8 plates. 8 plates to complete the total circumference of the shell. Now let's close this calculator, and now let's add 8 meters. Define the first plate length, and from here the start angle, let's make it 13 millimeters, for example, and let's click on update. Now the length of each shell course will be calculated here. Now, if you would like to define one of those with a different thickness, or a different length, like this one was 3 meters length, the second blade, and the fifth blade was 400 millimeters and 50. Change the thickness for each blade, so it's 12, and here it's 20, 12, 12, and for this one it's 60 millimeters, and for this one 12, 12. So you need to define the thickness for each shell blade. Now click on upgrade. Okay, you configure that the last one is greater than the delivered blade dimension. So we need to increase the number of segments here, as because we have a blade here with 3 meters, another one with 4.5. So the total length of all blades less than the total circumference. So we need to increase the number of segments like that. And for that one, let's make it meters and change the so one and recalculate. Now the last piece will be calculated automatically. Now we have 9 pieces for this shell. So let's recalculate the and click on save. Now when you click on start assembly, we will generate the first shell course from different pieces and thicknesses. Okay, we have 2 different pieces with a different thickness here. One of them is 20 millimeters and the other one was 16. Now the blades of this bottom created. Like that. And as mentioned on the previous session, here you can find a gap here. That's because that's the only type on shell you will need after creating the 3D model. You will need to make an update grade again to recalculate the actual neutral diameter, because we have different thicknesses, so the neutral diameter differ from blade to another. So after creating the 3D model for that type only, which is different pieces and thicknesses, you will need to click on update grade and save to reflect this modification and get the accurate length for each blade. Okay, now after modifying this part, we will add the anchor chair and discuss the available types of anchor chair and how we can add a washer to the anchor chair, how to add a rebad for the anchor chair, how to use the anchor chair for a tilted vessel. Here that's with a flat bottom. Now let's create a chair. So by selecting the shell blade from the tree and open the bottom, you will figure that you have different attachments you can add. One of them is the anchor chair. So if you select the anchor chair, like that, and click OK. Now you have this piece, and you will find 3 different options for the anchor chair. The first one, which is anchor chair with a blade. The second one with a complete ring. You have a complete ring instead of top blade. It's a complete ring. And anchor chair suits the sloped shell at the bottom. So for this type of anchor chair, you will need to define each one separately, because you have a different levels for the anchor chair. As mentioned here, for the if we make a sketch like that and make that's the bottom of the tank. Let's delete this. Okay. So here, for example, if you have an anchor chair here, the level of this one will differ from the second one, from the third one. So you need to define each one separately if you have a bottom, tilted bottom for the tank. Now let's select the first one, which is anchor chair and define the width, which is dimension A. So based on the image dimensions on the right-hand side, here if we take a look to the image here, you will need to define the dimension C, which is the projection of the top plate, dimension A, the slot hole and the spacing between the ribs, the bottom projection of this Anchorage chair, and if you have a washer, you can select between a rectangular washer or circular washer, and you can add a rebad by selecting this checkbox, which is wear blade activation, and define the wear blade from here. Now let's come back to SEG and define the A value, B value, which is the end width here, that one, the value here. Okay, so let's come back here and fill the dimensions here. The projection of this one, which is dimension C at the top, and here that's the edge, is the straight edge here, offset diameter, sloped bottom, and for the over thickness, if you have an over thickness for one plates, if you create a separate Anchorage chair and you would like to make the location of this Anchorage chair, it takes another radius, you can define the over thickness plus the thickness of the shell, define it here on this value, and that's the height of the rib. The orientation, here we have we can define the number of the Anchorage chair, but right now let's check the other dimensions. So for here, for the dimension B, which is the projection, we will make it 60 as the annular plate. The rib spacing, make it 100, and that's the rib thickness. And if you would like to add a wear plate, you can add it from here to find the height, width, and thickness for the wear plate. And if you would like to add a circular washer or rectangular washer, you can add it from here. So select the rectangular washer or circular washer and define the washer outside diameter, washer hole diameter, and washer thickness. Now you can define the number of Anchorage chair. Let's make them 12. So to calculate the orientation of the first one, if you make it 0, so the first Anchorage chair will be at 0, and if you would like to make it with an angle with the center line, so we need to calculate the angle, so it will be 15 for the first one. And now if you click on save and click start simply, you will create the Anchorage chair with the mentioned dimensions. Now let's decrease the thickness, the diameter of this washer a little bit. This 1, 2, and click on save. Let's click start simply. And as mentioned, you have two options if you would like to make a circular washer or rectangular washer. Now you have the anchor chairs arranged along the diameter of this tank. And if you take a near look here for the annular plate or the Anchorage chair, which laid on this plate with a different thickness, if we make analyze interference to check the interference between that one and that one here, you can figure that you have an intersect here between them because the diameter of all Anchorage chairs are the same. So during the creation of this part, you will get the thickness of the main blade for the shell with the original thickness, which is 12, not the 20 in that case. So in that case, you can make suppress for one of those Anchorage chairs and create another anchor chair with a different information here and at the same angle, but that time you will make an over thickness for that one. Okay, so from here, if you would like to select this, so here we have this one. So this one you can suppress it, okay, like that. So you can, which is number 8. So if we double click on that, and the number 8 you can suppress it, which is that one. So you can remove it from the assembly and create another one, and instead of it at the same place with a different diameter or with a different over thickness here. So it will be appear in your model, and in that time you will need to make another level of detail. So you will need to create another level of detail which not include this anchor chair. Okay, now let's click on undo. And after creating this anchor chair, you can make another type with a top ring. So let's remove this one, okay, and click on save. When you remove the wear plate and click on assembly, now you will be able to remove the wear plate at the back of the anchor chair, like that. There is another type for the anchor chair with the top ring instead of top plate. So let's add another anchor chair. So from here, let's add anchor 2. And for this anchor, let's select type 2 with a top ring. From here, let's add a circular plate, circular washer, change diameter, the same number, the same orientation. Let's change the orientation angle. Let's make it on degrees, for example. And let's make a change here for the height, the rib height. Let's make it and click on save. Now, when you click on start assembly, we will get a complete top ring for the anchor chairs. So sometimes you may need to use that type of anchor chairs with a top ring, like that. Okay, instead of splitted plates. And the third one, as discussed, it's used only in case of have a tilted bottom. So now let's delete the anchor chair 2, and let's add a clean outdoor to this plate, which was dimension with that dimension, with the length of that length. So from here, let's come back to the SEG, and from here let's select this one, the shell, and pick the part number 2, and you can figure that you have here the mid angle. If we take a print screen here and this one, we come down here and this table again. For the part 2 here, as you can see, we have the start angle, end angle, and mid angle. So the mid angle of this plate at around 90 degrees. So we can add a clean outdoor at this plate at the middle. So from here, let's select can 1, and from elements, let's add a clean outdoor. And from the clean outdoor, you will find 3 different types. The main difference between them is the Davit. The same options for each one, but the main difference between them is the Davit. The first one with small size of Davit, and the second one with that type of Davit. The third one with that type of Davit. So let's select the first one, for example, and select the 24 by 24 or 36 by 48 size, and here you have the height and the all information about this clean outdoor based on the API. So the information here, which is the height of opening, width of opening, all of that will be related to the API. If you would like to make a modification on that, just select user defined dimension, and you can figure that those cells will be opened, and you can modify the dimensions if you have something in your calculation and you would like to make a modification on that. Here for after modifying those dimensions, you will find a value here for the overhead or shell over thickness. Okay, here this plate with a differ thickness, if we measure the thickness here, it's with 20 millimeters. So the origin plate is 12 millimeters, and so you have 8 millimeters differ from here. So you can increase the over thickness with 8 millimeters. Okay, because this clean outdoor will be located at this plate. So if you keep it 0, you will get the inside diameter of the reinforced bed, and the neck will be located on the origin outside diameter of the shell, not the actual shell with the greater thickness. So you will need to define the over thickness here, and here you have the neck thickness, the bed cut clearance between the neck or the clean outdoor neck diameter and the inner of the reinforced band. So that's the clearance between them. Here's the projection of the clean outdoor, and here you will need to define the orientation, which is around 90 degrees. Okay. And here the user defined dimension, as we discussed, you can make a manual modification here for those values. Now here the rebad thickness, rebad material, flange material, and the other flange material, flange thickness, gasket thickness, cover thickness, all dimensions you can modify it from here. And finally the opening direction. If you would like to reverse the direction of opening, for example, here if you would like to reverse Davit direction from that side to the other side, so we can mirror it on the other direction, so it will be on that side, not to the previous side. Okay, now let's click on save, and you can define the set weld detail of this manhole, so you can change the as a single V or double V, make it cladded or not. So in that case, it's a no clad and single V. So let's define the dimension of the weld, A and B. And now let's click on save. Now when you click start assembly, we will generate the clean outdoor at this plate at 90 degrees. So that's the neck of the clean outdoor. The rebad, flanges, gasket, the cover. After that, the tightening bolts, tightening nuts, after that the clean outdoor Davit. Now we have the clean outdoor located here, and you can figure that you may need to change the orientation a little bit. We make it 90 degrees, and actually it should be at 91.3 to make it actually on the middle. So we can change this value a little bit here. So if we come back here and change this value and click on save, now at that time it will be on the middle. So let's click start. Okay, now you can figure that the clean out door becomes centered to the this annular plate. Okay, and you can adjust the orientation of blades from the form here of the shell, so you can modify the lenses to adjust the center line of it to make it exact number by controlling the start angle and each plate. Yes. Now let's add another part like a nozzle with a deep pipe on this shell to make it located on a bottom plate here. So from here, let's select this can, and from that one, let's select. You can figure that you have nozzles according to ASME and the nozzles according to the API. So let's select nozzle according to API with external and internal projection. So you have this type and that type. Type B, which is nozzle with internal and external projection. So let's add N1. Okay. And the N1 here, we will make it as a pipe nozzle from pipe, so the neck will be from pipe. And let's select the size of this nozzle as 4 inches. Here's the pipe diameter and the other dimensions of the rebad based on the API. And here the low type minimum dimension, which is 150. That's the low type dimension. You can select between different options for the circular bed. You can make it diamond with low type or diamond only, or circular with low type or circular only. For here, let's make it diamond low type, so it will be welded to the annular plate, not as a diamond plate only. It will be in up to the end. And from here, you can define the location. So the location should be greater than the low value. So let's make it on 100 millimeters, for example. And the orientation, let's make it on 5 degrees. Okay. And the projection of this one, let's make it on 150. And the internal projection, let's keep it 200. And from here, let's define the surface of this one as plane. And if you have any nozzle load, you can define it from here. But right now, let's save this one and let's add an external connection as a flange. From here, let's add a flange. So N1 flange to this nozzle. And you will find a list of standard flanges. You can select the suitable type for your case. In our case, let's select slip-on flange rest face according to ASME P16.5. Select the rating and the size. Size will be 4 inches, and the offset from the rest face, let's make it 5 millimeters, and let's click on save. Let's come back again to the nozzle and change the scalable of this nozzle. Let's make it 40 instead of standard. They will be the same in that size, I think. The standard and 40, they are the same thickness in the size 4 inches. And after creating this, if you open the calculator to calculate the projection of the facing of this nozzle from the center line, at this point we need to discuss it. So from here, let's take a print screen, and from here, let's find this. Here you have a value for the define the projection from the center line of the tank to the facing of the flange. Here we have the flange outside diameter. It will be like that, okay. And so the half value of that one will be divided by 2. So that's the half value. And you will need to make a projection from the facing of this flange plus that value is 300 millimeters. So the projection from the center line will be like that. So we can make it 730, 7,300. So we can change the projection from here with that value. So if we open that value like that, 7,300 and click calculate. Now the projection of the pipe will be calculated automatically here. If we come back here to this form, if you click on calculate, you will get the actual pipe length that you will need, which will give you the so this value will be reflected here for the projection, which is that one. Okay, so here this value will be reflected on projection of the pipe to outside. Okay, so this form gives you the ability to calculate the actual projection from the vessel center line, and it will be important in case of pressure vessels and columns heat exchanger. Maybe not in storage tanks, it's very important. You can define the projection only, but here if you would like to calculate it from the center line, just calculate and click on save. Now after click on save, you can figure that the projection value will be reflected here. Now when you click on start assembly, you will start creating this nozzle with a rebad as a diamond low type. And here the sleep on flange of this nozzle, like that. And now let's take a look from the inside. Here we have the inside projection of this nozzle. Now we would like to make a connected flange with another pipe. Okay. After that, making an elbow. So if we take a look like that, we need to make a pipe here and make a sump at this point. So let's make an connection point at the end. So from here you can add a flange connection. So in one flange, so it will be two flanges with a gasket in one time. From here, let's select slip-on flange like that. Select the size, define the offset, and now here you can figure that you have flange 1, flange 2, and the gasket, and you can add a bolt to this one. So with let's select this one, and from bolts, let's select stud N1 stud like that, and from here you can select UNC, and if we open the Trouvé to check the size with that one. For example, if we open the Trouvé from here, and for flanges and for binding, sorry, for bolts, here, if we take a look, is 550 with 4 inches nozzle. So the bolt size will be 5 by 9, and the length will be like that, 90. So let's come back here, 5 by 9, and the length will be like that. So it's the standard. You can change the material and for nut and bolt. Click on save. Now let's create this simply for the connected flanges. Now, as you can see, we create a connection or a connective flange to the end of this pipe. Now let's add a deep pipe, another deep pipe with an elbow. So let's come back to SEG and let's select the internal connection. As mentioned, by selecting the internal or external connection, you can add items. You have the ability to add items after the that point. So from here, let's select N1 pipe. Let's add another element. And here we have this pipe. Let's make it 4 inches. Scalable 40. and from here let's define the length as 300 millimeters. For that, let's add an elbow. So from here, let's add elbow and one elbow. And after selecting that, let's select it as a long radius, 90 degrees. Select the size schedule and click on save. Now when you click on start assembly, we will have this pipe and an elbow like that. You may need to increase the projection of this pipe a little bit. Let's make it, instead of 300, let's make it 700, something like that. Click on save. Now when we click on start assembly, we will change the length of this pipe. Okay, we may need to increase it a little bit. Okay, let's make it 1 meter. Click on save. Now after modifying this, let's add a sump at the bottom. Okay, so to add a sump at the bottom, we need to define the offset of this sump from the center. Let's make a quick drawing. So from here, let's open drawing like that, and take a top view for this one. Okay, let's add a center line. Okay, we have this center line. But let's add another center line for the elbow here, and make the center line here, as mentioned, and make it aligned with that edge. Okay, now we can measure the center from here to there, which is the offset of, will be the offset of the sump. So that value, in that value, will make a sump with that offset to suit. So you can make this value accurate value by increasing the pipe length. So for example, we will increase the pipe length with 33.27. So let's come back to the pipe from here and increase 33.47. Is that right? 27, sorry. 27. And click on save. Now when you click start, the offset of the sump from the center line will be with the accurate value. So it will be like that. So the offset will be 5 meters, 0.6. So now let's come back to the bottom plate. So here we have the bottom plate, and if you open the elements, you will be able to add the nozzles. So from here, let's add a nozzle as a sump. And for this sump, make it as a nozzle from plate instead of nozzle from pipe. Let's make it a nozzle from plate, and let's define the nozzle from plate. Okay, so let's define the outside diameter of this one. Let's make it like that. So that's the outside diameter, the thickness, longitudinal welding line orientation, and here we have the longitudinal gap. By the way, it's very important to define the gap width. If you have a single part, as a plate, you should have a value for the gap. If you define this value as a 0, SEG will not be able to draw a part from plate without any gaps to create a sheet metal development. So you should define any gap for weld if you have a single part. But if you have a multi-part, it's no problem to make this gap at 0. But if you have a single part, as mentioned on the third session, which is the sheet metal session, if we make, for example, if you make a circle like this and try to make a flange contour like that, you will not be able to select this flange. You should have a gap. So again, if we make this a circle like this and make an arc, like that, which defines the circumference of this shell, you should have a gap here between the end and the start. This gap will give the ability to make a sheet metal for the part. Now, if we try to make a contour for this one, you can figure that you can draw this part and get a sheet metal development for it Without this gap, you will get an error. No part will be created. So you should take care for the parts which created from a single sheet metal plate. So here you should give a value for the gap. Now let's define the offset. It's 5,600, and the orientation will be the same orientation of the nozzle. So I think the orientation of the nozzle in 10 degrees. So let's save this and come back to the nozzle. Check the orientation. The orientation is 5, not 6. So let's come back to the sump and define the orientation to be a 5. And here the projection to the bottom, let's make it 600 and make it seat in or seat on. You can add a rebad or insert bad. Define the width, define that as some, okay, and save it like that. Now, if you read this sum, you will get the configuration of the sump, and we will need to add an end plate to this sump. Okay, we have the rebad. Now the sump is centered with the with this elbow. We need to add an end plate here. So let's come back here and select the external connection of this sump, and let's add an end plate. So you can add a flat head from here, or you can select one of the end plates here, that one. If you select end plate like that, you can figure that you have the ability to add different types of end plate, like a rectangular end plate with bolts, rectangular end plate only, a rectangular ring with bolts, or circular plate without holes. So this one suits what we need. So from here, let's add the outside diameter of this one. The pipe outside diameter is like the pipe, and let's increase 50 millimeters from each side. So let's increase like that. So that's the outside diameter. So you can take that in your mind during data entry. So let's increase it, make it like that, and make the thickness of this one, keep it 14. And now let's click on save. Now when you click start assembly, we will add a bottom plate to the annular plate, sump opening. Okay, now we have this sump at the bottom of this tank, and now let's make a section here. So from view, let's take a half a section view, and for this pipe, if we let's open the elbow from here and select one of the origin planes to make a half section here. Now if we take a look to that plane here, let's rotate it like that. Now we need to make a deep pipe here after this elbow. After that, make stiffening for it, or make support ribs for it. So from here, let's select the inlet of the nozzle N1, which is that inlet. We need to add another pipe after the elbow. So here we have the this nozzle with internal connection. We add a connection flange, add a pipe and elbow. After this elbow, we need to add another more pipe. So from here, let's come back and select the inlet. From elements, let's add a pipe. So N1, pipe 2. Okay. And you have the ability to make it looks like another pipe on the same level. So from here, if you open this list, you can figure that you have N pipe 1. So if you select it and select this option, which is select part same as, and click on create, it will be located on the same level, which is here, and takes the same information, which is pipe with 4 inches and the same schedule. And from here, you can change the length of this pipe and click on save. Now, when you click on start, you will get the pipe here with internal projection inside the Sump, like that. Okay, now let's add stiffening, longitudinal stiffening rings to this one. So from here, let's select this pipe, and from external attachments, let's select long blades. Okay, and from long blades, let's make one strips. And based on this one, you can add on this configuration here. You can add the long blades. You can add BFC or UBN channel along the pipe with those different configuration inside or outside. But in that case, we select external connection, so it will be like that. You can make it welded to the outside by that way, or a longitudinal by that way. So let's take a screen. Here, that's an external connection, UBN or BFC. So you have a case one option. You can weld the UBN in that case with that direction or with a flipped direction. You can make it welded directly to the pipe by that way, or from outside by that way. So you can select those edges welded to the pipe. You have different options in case of using external UPN. In case of using internal UPN, you can select those shapes, those cases. So from here, you can select the case of which suits your requirements. In that case, we will use the long blade. Okay, so in long blade, if we do this, and for the long blade, if we you will be able to define the blade dimensions, which is width and length. So from here, you will be able to define the length and width, and here the location of this rib from the center line of this one. So the location defined from the center of this plate up to the start of the main part, which is the pipe. So now let's create a ring, a long ring, stiffening ring along this pipe. So from here, let's define the height as 50 millimeters, the thickness as 8 millimeters. The location will be at 100 millimeters. The orientation 0 degree, and the width of this one, let's make it 200. So let's increase this one to 500 like that, and make the quantity around that one as 3 pieces around the pipe. So when you click Start Assembly, and after creating this, we will need to adjust the location of the pipe to make this rib located on the end blade of the Sump. After creating it like that, we create those plates here. We have 3 plates. Here we have 3 blades. Because we take a section, one of them is disappeared. So to measure the distance from here to there, to modify the location of the this one up to the end, so we need to increase the location of this ring. Here we need to move this plate down here to lay it on the end blade of the tank. We need to increase the location of this one with 56. So let's come back here and increase the location with 56. And now let's click on Save. Now when you close this form first, after that, let's click Start Assembly. And as you can see, a zoom extend takes place when you make an assembly. This option we discuss it here, which is on the app setting, which is the normal zoom or zoom out automatically. So if you select normal, now when you make a zoom like that and make a modification in anything, like changing the orientation to make it, for example, 5 degrees, like that, or 0 degree, 90 degree. And click on Save. Now when you click Start Assembly, the zoom out will not take place when you make the assembly, so the view will keep as it is, no zoom extend automatic. Okay, unless you make the zoom by using the orbit option or using the cube view cube. Now let's make it 0 again and click on save, and from setting let's make it zoom extend again and click on save. Now here we made a sump with a deep pipe on this bottom. Okay, and let's remove the half section. Now let's add a manhole to this course, and for example, let's check the orientation of this one. Let's make it on 60 degree. Okay. Let's select the shell, and from elements, let's select a nozzle according to the API, but with external projection only. So from here, let's select M1. From N1, let's define it as a nozzle from blade. Define the size as 24. Make the this rebad as you can make it as a diamond bed or diamond bed with low type. Okay, as manway. Here define the thickness, longitudinal building line orientation, gap, the location. Here you can figure that the location should be higher, more than the low type defined by the API. Here it's defined by the API as 630, so we can make it as simple. And the orientation is made on 60 degrees. The projection, let's define it like that. Click on save. Now let's add a flange to this one. So M1 flange. Okay. And for the M1, you can select between standard flanges, and in our case, let's select nozzle according to API, select the size and change the thickness. Let's make the thickness as 14 millimeters. Here's the dimensions of this flange. Click on save. Now let's add a gasket. So from here, let's add M gasket. And let's make this gasket according to the API. Keep the thickness as it is. If you would like to change it, you can do. Click save. Let's add a cover. So from here, let's M1. And this cover will be according to the API. So let's select API cover and change the thickness rather than the standard thickness here and make it flipped. Click on save. Now let's click on start assembly to start creating the manhole. Okay, after creating the clean outdoor and manway of this nozzle, let's add some attachments like the stud bolt. So from inspect here, the hole diameter is 33 and the gap thickness between bolts is 36 between 0.5. So let's add a stud bolt with this cover. So from here, let's add stud bolt and stud. ISO knot, define the diameter of the bolt. Okay, and from here define the length 36.5. Keep that. Let's add a hand grip. So from here, let's M1 grip, and here let's select the suitable type. You can figure that the hand grip will be welded directly to the cover. And from here, it will be on the outside diameter of the cover, not to the face. And for that one, it will be to outside, but straight like that. So you can figure the difference between type 1 and type 2, the hand grip rod will be takes this direction. So from here, let's keep those dimensions as they are and just change the orientation of this one and save. Now let's start the assembly to create the stud bolts and hand grip. Okay, so let's change the location of the hand grip from here. So here that's the length, width, the rod diameter, and the extension. And here we have the offset. So it will be with no offset, and the orientation will be at 0 degree. And click on save. Now let's add one more part, which is the Davit. So from here, that we can discuss it in detail, inshallah, on the pressure vessel part for the manhole Davit and manhole Davit in detail. And as a quick view for that, for the manway Davit, for that type, you have the ability to create a Davit as a part. It's not in detail. So it will appear on the 3D model as a single part. No details in bill of material, just a Davit. It will be appear as a Davit on the bill of material. So the orientation, let's make it 180 and click save. Now, if we open the bill of material like that, you can figure that you have a Davit like that as a single part. No details for this Davit. You have a Davit for the clean outdoor and Davit for the manway. Okay, but if you would like to make this Davit in detail, in that type you will need to create a detailed Davit, manway detailed Davit. In that one, each part will appear on the bill of material like clips, rod, pipes, eye bolt, nuts, all of that will appear in detail on the bill of material. For that case, let's select the hinge one and click on Start Assembly. To start creating the hinge and manhole hinge, and here we need to change the orientation of this one. So let's come back here and move this flip and come back to this one, and let's click on save. Okay, sorry, we can make opening direction, change the opening direction to flip the direction of the this one, which is the hinge, make it on the other side. So to flip it on the other side, let's make the opening direction on the other side. Now when we click simply, you can flip the direction of this one to the other side. So if you take a look here, okay, I may need to check this. Okay, right now let's create another part. Let's create another shell plate. So from here, let's select the vessel, and from elements, let's add CAD 2. Okay. And for CAD 2, let's select in this time shell from different pieces only without thicknesses, and define the inside diameter, height, millimeters. Here you can define the gap as 0 because you will have a different blades, not a single blade. But if you have one single weld line, you should define a gap for it. Okay. Now let's define the number of pieces. Define bends here and make update grid. Now the last one will be calculated. Now let's define the start angle of this one and click on save. Now if you click on start assembly, we will generate the second shell model. Now we have the second shell. And as mentioned previous, for the longitudinal welding line clashes, actually you have the 3D model. You can make a visual inspection to check if you have any issues with the welding lines or not. So for example, you would like to measure the distance from here to there. By using the measurement tool, you can measure the distance between that line and that one. And you can decide if you would like to make more change on the orientation or not. You have here 665. So you can decide if you would like to increase this value or not. The same thing here, the orientation difference between that line and that one. Now let's add another can. So from here, let's close this. And from here, let's add another can 3. And make it looks like can 2. Okay, to avoid data repeating data entry again, and just click accept. And from here, you can figure that it takes the same type, the same information, and just you can change the thickness if you would like, and you can change the start angle. So, for example, if you would like to make an offset with 1.5 meter, to make that as discussed from the setting, you can open the calculator, define the neutral diameter, and here you would like to make the arc length difference as 3 meters, for example. So you will need to define the angle of the start angle of this one with 3 meters. So if you take a copy here and put this value right there. Now if you make a recalculate, the longitudinal welding line orientations will be changing. Now if you click on start assembly and take a look from the front view, after creating this one, let's see this one first. Okay, now we have the third course. If we take a look from the front view, okay, here we make this the first line here, okay, on this shell course. So how I know that is the first welding line. When you select this assembly and open the assembly of this one, and go down here and select the first part. Here you can figure that if you take a look from the front view. Here, that's the first part, and the first part longitudinal welding line orientation, which is that line, will be located from the center, from the 0 level. Here, if we take a look, let's make a print screen to describe this. Comes here. That's the front view. Here, the 0 degree and 190 degree on the back. On the front, here, the 0 degree. And on that side, the 90 degree and 270 on that side. So here it's 0, 80 on the back. Okay. Here it's on the front. Here, and in that side, it's 90 degree, and in that side, 70. Now, if you take a look, we define that we need the longitudinal welding line orientation of this one, which is that one. Okay, the first longitudinal welding line will be located with 3 meters offset. If we come back here, we calculate the angle, which is that angle, which will give us 3 meter offset from the 0 degree. So if we measure the arc length from here to there, the arc length, it will be 3 meters. Okay, so from here to there, if we take a look from the top view like that, okay, so if we measure the arc length from here to 0, it should be 3 meters for this part. So by that way, by using the calculator on the setting, you can define or calculate the required arc length, or by using the arc length and the diameter, you can calculate the angle to describe the start angle of the weld. Now here, the other parts of the can, you can get it from the simply form from that side. Now let's create another can. From here, let's add can 4, and make it looks like can 2. Okay, and click on add. But for that time, we will change the thickness. Let's make it 8 millimeters and recalculate again the angles, because the thickness changes, so the neutral line will change, and that will affect the angle of that one, and will make the last piece will increase. Now let's click on save, and let's add another can, which is can 5. Can 5 is the final can, and let's make it looks like can 3. Okay, and let's change the thickness and make it 8 millimeters, and make the final height only instead of 150, and click on update to calculate the angles and the final plate length. Now let's click start assembly to create 4th and 5th can. That's the 4th can. Okay, now we create the last can. Let's add the compression ring and add the roof plates. For this one, after adding the roof plates, we will create the spiral stair and discuss how to add multi-levels for the spiral stair, inshallah. But right now, let's add the compression ring. So from here, let's select the equipment. And from elements, let's add from the API tab, let's add a compression ring. And for the compression ring, let's select type B. Define the outside diameter of the bend, which is the outside diameter of the tank at the top. So if we measure it, the radius for the outside from here, you can get it 14.0116. So let's put it here, 14.0116. And the offset from the top, let's make it 10 millimeters. Select the standard and select the size of the angle. Let's make it 120 by 100 times 120, and with second thickness 12 millimeters. Now let's click on save and start creating this compression ring. Okay, now let's create the roof of this tank. Okay, now we have this compression ring like that, and if we take a half section, let's take a half section like that and take a look closer from here. You can get that you have this configuration for this compression ring at the top. Now let's remove the half section and let's create the roof. So from here, let's select the equipment and let's select a ranged roof, okay, which includes the blades, and define it like that. And for the top opening, let's make it like that. Define the thickness as 6 millimeters. Define the slope as 125, and the overlap. The inside diameter of the tank, we can calculate it like that. We have the outside diameter of this tank like that, and we need to increase it a little bit from the two sides to be overlapped on the compression ring. So let's add 100 millimeter. So the value could be around that. So we can make it 14 and 120. So it will be like that, 14, 120. And the torch cut tolerance, we can make it 0. And from here, let's increase the scale a little bit. And now let's draw the blades. And let's change the scale a little bit and click on save and draw blades. Now we have this circle. Now if we click on draw, we will get this configuration. We can make it all centered as discussed. So from the set grid, we can make it all centered and draw. So we will get this configuration. Or we can make it without using any center options. So you will get this configuration. If you would like to make some adjustments, like make this plate as a half plate or something like that, you can do that. And the same, you can make this one as centered. After that, make it as a half plate like that. So you can change the arrangement of plates by that way. Now let's change the longitudinal welding line orientation. For that one, if we take a look from the front here, we don't have a weld line at 0. So we can make this weld line at 0. And from here, let's click on save. Now let's click on start assembly to start creating the roof plates. So you can figure that if you take a look to the image, to the tree, construction tree of or the model tree on the right hand side, you can figure that the number of blades generated for this roof, and you can imagine how much time you will spend to create that manually. Here, the part sketch modeling and assembly created in seconds. After creating this roof, inshallah, we will make some attachments for this roof, like end plate, add some nozzles. After that, we will proceed with this spiral steering. Okay. After creating that, SEG will make some calculations and import this assembly of the roof to the final model of the storage tank. Now, as you can see, we have the roof plate arrangement for this tank. And now let's add some parts at the top. So let's select the roof, and from elements, let's select roof cover plate. From here, let's select this part and define the thickness of the blade and the radial blade overlap. Let's make it here, which is the dimension O. And for the radial blade length, the longitudinal welding line orientation, let's make it on 90 degree. And for the weld gap, let's make it 2, and number of plates, let's make 2, and let's add a top plate with 6 millimeters at the top, and let's click on save. Now let's add some, let's add a nozzle with internal projection. So from here, let's select a nozzle type B and create a nozzle as N2 as a roof. From here, let's select it as a nozzle from pipe. Define the size as 6 inches with the scalable, let's say 160, or let's make it 40 millimeters, and define the offset to be, let's say, 6 meters, and the orientation, let's make it on, let's say on 0 degree, and the projection, if you take a look, the projection will be calculated from the seam line, which is seam line at the top of the compression ring. Okay, so the projection, we can make it, let's say 400, and the internal projection, let's keep it with that value. Let's add a rebad, define the rebad diameter, and let's say water inlet. And that's the description, or the nozzle service, and I click on save. Now let's add external connection to this one as a flange. So N1 flange, and for this one, let's add weld neck raised face flange according to ASME. It's 6 inches, the same schedule, and click on save. Now when you click on start assembly, you will generate the 3D model for this. The first thing, the cover, roof cover with an end plate. After that, the top nozzle. With a rebad. Now the connected flange at the outside. As you can see, we have this nozzle here at 0 degree. We can increase the offset a little bit, and right now we can make a half section to check that nozzle. Here we have this nozzle at that location with internal and external projection. Now let's increase the offset a little bit with a half meter and make two connection flanges here with a deep pipe. After that, we can make a clips, which is support for the internal support pipe. So let's increase the offset of this pipe a little bit. From here, let's make it like that, and click on save. And at the inlet, let's add connected flange. So in two flanges section. Okay. And here, let's select this flange and make them as a slip-on raised face flanges. Select the size, make the offset as 10 millimeters. Let's add a pipe after this one. Make N2 pipe. Okay. And from here, let's select the pipe, and from this view, select the size of the pipe and select the schedule, define the length. So let's check the required length. We can measure the required length from here to the bottom, nearly around 6 meters. So let's make it with 6 meters. And click on save. Now let's start the assembly. To update the nozzle offset from the center line and connect this nozzle with 2 flanges at the inlet. After that, a deep pipe with 6 meters length. By the same way, you can add a stud bolt for this flange, like what we did with the drain pipe. So now we have a pipe with internal projection, like that. Now let's add a support clip. So from here, let's select can 1, and from elements, let's select the internal attachments. And for here, you can figure that you have 2 different types of pipe support. One of them is pipe support with guide and pipe support by clip. Let's select the first one here, support. To check the configuration of this one. If we take a look at this one, you can figure that you can make a support like that. Okay, with if you have a welded, let's take a print screen for this and discuss the details. Here, it's so by using this one here, sorry, you can add a rebad inside the tank or the vessel. Define the offset for the pipe from the vessel center line. Okay, and if you have more than one pipe and you would like to make a multi U-bolt connection, you can use that type. Okay, but if you have a one guide, you can define the number of pipes as 1. But if you have more than one pipe barrel at the same level, you can use this support for multi pipes. Okay, and you will need to define the pipe offset from the vessel center line. Okay, and the second type here, we open it and take print screen. Take a look. Instead of the rebad, you may take that connected from a welded flange to the shell. So you will have a flange here welded directly to the shell instead of a rebad, and that will be connected with a stud bolt with another angle, and here you have a U-bolt connection. Okay, that's a type of the support pipe. Let's add another type, which is from internal. Let's add support clips, which is support. Okay. For this type, you can make a support clip. By that way, you have a clip directly welded to the pipe. Another clip will be welded to the shell, and you can define a contact angle like that. So you have 2 segments of plates and a connected angle between those plates. One of plate connected to the pipe, another one connected to the shell. So let's use the first clip, which is that one. Okay, and from here, let's select the first type. Define the angle size. So let's make it, let's say 7 times 7 angle, and from here let's the extended length, which is the length after the pipe, let's make it 150, or let's make it 200 right now. After that, we can change if we need. And from here, let's define the location from the bottom. We will make the location from the bottom. Let's make it a start and at 1 meter, for example, and the orientation at 0 degree. The axial angle of this one, no axial angle, and here it's the pipe diameter. So let's measure the pipe diameter from here. Let's measure the outside diameter of the pipe. So let's measure the outside diameter. Sorry. From here, let's measure the outside diameter. So let's take this value and put it here, which is 6 inches pipe diameter. And the pipe vessel offset from the center line is 0. Pipe horizontal offset, which is the pipe vertical offset, it's 500 millimeters, because we make the offset of the pipe with 6 meter 0.5. Okay, so the offset from the inner surface of the vessel will be 500, and the pipe offset from the horizontal is 0. Now, if you would like to add a weir plate, you can define it from here and define the weir plate thickness. Let's say millimeters, for example, or let's make it 6 millimeters. If you have a fillet, if you would like to add a fillet to the weir plate, you can add it from here. And here the U-bolt size, and to add a rod extension and the number of pipes. You have one or a single pipe only, and the pipe spacing. In case of one pipe, no need to define this one. And here, if you would like to add a double knot after on the U-bolt, you can define it from here. Now let's define that by that way and click on assembly to create this one. Okay, here if we remove the section or make it offset a little bit from the center, let's move it a little bit like that and click on OK. You can figure that you have the pipe support for this nozzle by that way, and you can repeat the number of that from SEG by the same way. And if you would like to make it from inventory, you can make a pattern for this, but in that case it will not be calculated on SEG bill of material. But for example, if you would like to increase it from here directly, like make it like that, so here, so you can make pipe support by that way, and easily you can detect the intersect with the welding lines without making a development for the blade, because you have the 3D model, and from the 3D model itself you can detect if you have any clashes or not. Okay, now let's proceed with the next step, which is making the spiral stair. Let's remove the half section, and now let's add the first spiral stair, and we would like to make it with a different levels, and how to describe the second or third or fourth or fifth level of the spiral stair. Here let's select the first can, and from elements let's select external, and from external let's select spiral. And for the spiral stair, let's select type A. And from type A, let's define the clearance between the inner stringer and the outside diameter of the shell. Define the thickness of the stringer, the height of this one, let's make it 3 meters, for example. Okay. For that, the width of the stringer, after that the start contact angle. Okay, the orientation, which is the start angle of this spiral stair. Okay, so let's define this one. For example, here if we open one of those images and reset this, here if you check this value, which is the start to contact angle, That means, for example, if you start creating the spiral stair, you will need to make this spiral stair on 45 degrees. So it will be on that area. So the spiral stair will be located like that on 45 degrees of the tank. So to calculate the arc length at the bottom here, if we open the calculator of the setting and defined the tank, let's say the diameter of the tank, and define the contact angle, which is 45. Here you can figure, let's define the angle here, sorry, and calculate the arc length. So the bottom or the circumference width here will be 5 meters, 0.5, around that value, 5.5. And the height here is, the stair height is 4 meters. So from here and there, you can calculate the spiral level angle. Okay, so you can decide if you need to decrease or increase the angle a little bit. So from here, we could decrease it a little bit, make it 4. And the start angle of this spiral stair, if we make it at 0, it will start at here at this point directly. So we can make it start at 0, no problem, and that's the height level. So we can make it offset from the bottom with that level. So the height of the spiral stair, we can define it like that, and the stair edge cut length, you can detect the values from the images here. So the stair cut length here, which is that area, and the you can define those values offset from base. Sorry, here this value not from the bottom. The offset from bottom, it is that value. So let's make it like that. And stair height at the end, which is that value. That's the stair height at the end. Here, radial offset stair height at the end, which is that one, which is the height, that value. If we take screen from here, which is that value, the stair height at the end, okay, which is the height at this end. So let's make it 200 millimeters, and the offset of the platform of the spiral stair from the bottom, the inside width of the spiral stair. Here, if you would like to make the spiral stair in a clockwise direction or counterclockwise direction, in our case, we would like to make it on the other side, so it will start from here and goes to up in that side, so it will be counterclockwise. So let's change it counterclockwise. The step width, step thickness, and step rise. Okay, and from here you can change the platform angle. So here, let's make this angle as if you would like to calculate it by the same way, here to calculate around the value. Here the angle, if we make it 6 degrees, so the platform will be with 700 millimeters from the inside, so we can increase it a little bit and calculate the length of the platform. Okay, so let's make it 7 degrees. Okay, and from here the current thickness of the shell, it's not 8 millimeters, it's 12. Sorry. And from here the wear blade thickness, if you would like to add a wear blade for the bracing. Okay, and wear blade length and width. From here the radial thickness of the blade, and bottom radial blade width, top radial width. Here some other parameters. Let's check that, which is radial cut to the first post. Here this option will give you, if we get the screen here and here to discuss this option. Those options here, if we This one, radial cut to first post. So here, if you take a look to the image here, that's the first post. Okay, so if you would like to make a radial cut at the end, you will activate this checkbox. Okay, or if you would like to make it with a radial without a radial cut, you can keep it as it is. If it's connected to another platform at the end, you will activate this one. So that means this platform will be connected with another one at the end. Okay, so those options you can activate them. So let's select radial cut to the first post. Okay, or keep it. And from here, let's change the post size, which is defining the angle of posts. The first post offset, the radial height, the number of posts per stair, number of posts per platform. So here, if you take a look to the platform here, so the number of posts here for the platform, 2 or 3 platforms, and the posts for the spiral stair itself, you can define the number of posts for the spiral stair itself, and post offset from bottom, the first post offset from bottom. Here, radial bended end. Here, if you would like to make the end with a bended radial at the from at the end from here. That's in case if it's not connected to another platform, you can select this option to make this platform with a closed end at the top. Okay, that's the description of the used ribs and bracing angle, the bracing angle size, and here the first bracing post. If you take a look here to this image, you have, let's take another clean shot. Yeah, let's take print screen. Take a look here. You have first bracing angle located here. So this angle, you will need to define the offset for this one. And if you would like to make a bracing angle to it, you have a channel here. And if you'd like to make a bracing for it, you will need to activate bracing activation. So by clicking on that, you will activate a bracing on this one. Well, the first one, it will be on a low level, so no need to make a bracing here. We can make a bracing from the second one. So let's come back here. And for the second one, we will activate the bracing, and here you can define the location of this bracing. Let's add another one at 3 meters and add a bracing for close platform end if you would like to close the end of the platform. Now let's save this one and start the assembly of this spiral stair. To add another spiral stair, here this spiral stair will takes a time during creation because it's include a large number of elements. As you can figure here, you have a lot of parameters you will need to define to describe the this platform. Sorry, is this spiral stair? A lot of information you will need to define it. So it will take a little bit time to generate this, around, let's say, 2 minutes or something like that, in 2 or 3 minutes to generate the complete spiral stair. After that, we will, inshallah, proceed with the second spiral stair.
That's the bottom rail and the top rail plate. Now the bracing parts, the channel and the bracing angles with the repads for the platform. After that, for internal and external stringers, they will be generated. Now I think that's the last piece for the bracing parts, repads. I think now it's done. And we will take it over the 3D model of the tank and proceed with the second spiral stair. And in that case, let's describe some important points regarding how to define the second, third, fourth, the other spiral stairs, how to define the levels and orientation of this one. Here, as you can see, we describe the offset of this spiral stair from the bottom to be 300 from the bottom. So the level from this line to the top of the annular plate will be 300. And now you can figure that you have this spiral stair located on the shell, and easily you can detect if you have any clashes with the welding lines of this vessel or not. Now to describe the second one, spiral stair, let's add another spiral stair. And so from here, let's select the can one. And from here, let's add another spiral stair. So it's external attachment. So spiral stair 2. And let's make it looks like spiral stair 1. And change some modify some dimensions here. If we take a look from here, as you can see, the start angle of this spiral stair starts at 0 with 40 degrees. So if we let's take print screen for this quarter like that, and go to this here. We start creating this spiral stair start at 0, and the end of this one start from here up to 40 degrees. So this value is 40 degrees. After that, we make this platform with another angle. So the center could be here. It's on that circle. So the center comes from here, nearly here. Okay, so we make this line vertically and another one from here to there. So this value will be 40 degrees. and for the end of the platform, it's here plus 40 degrees plus the platform angle, which is 7 degrees. So here, that's the end angle of the platform. Okay, and so to make another platform, so to define the start angle of this one, we need to make it little bit to inside here. Start with let's say 200 millimeters inside this one. So we need to describe this value. So if we open the calculator and from here calculate the inside diameter of that one, plus let's say around 800 millimeters, which is the spiral stair width. So calculate this value. So millimeters plus that value, okay, around 15 millimeters, 6. So it's that, and here we need to make it with 20 millimeters. So we can decrease the angle of start angle of the second spiral stair with 1.5 degrees from the total angle which we calculated here. Okay, sorry. Let's come back to this image. So the start angle of the second platform will be 47 minus 1.5. So it will equal 5.5 degrees. So that's the start angle of the next platform. So from here, let's come back to SEG, close this one. And for the second spiral stair, so the contact angle here, let's say so the start angle here will be 45.5. And the contact angle, we will change it based on the height that we need. So we need here, let's say, from here to there. So from tools, let's inspect the remaining value from here to there. We need 2 meters 0.5, around 2 meters 0.5. So from here, let's define the height of the spiral stair to be like that. And for the contact angle, which is 40, it could be the half angle of the previous stair, which is, let's make it 25 degrees. Okay, and for the spiral stair height, the offset from the bottom, if we take a look to that one, the level of the second spiral stair, let's take an image from here to there and print screen. Let's put it on another. So the second spiral stair will start from that level. It will start from here, the end of the second one. So we need to define the offset from the bottom. So the offset of the bottom is the height, which is 300 millimeters, which is the offset of the first spiral stair. We have 300 millimeters here, and plus the height of this one. Okay, so we need to define this, the offset from that one to be 4 meters and 300 millimeters. Now let's remove the radial end to remove this one. And from the option here, let's make it closed at the end to make the platform closed at the end. And let's remove the third bracing and activate the first bracing at the bottom, which is the first bracing located here. We have this image. For the second spiral stair, it's on another level. So the first, bracing UBN here, we could add a bracing beam to it because it's on another level, not on the ground. Okay, so from here we could change this one to, let's say, 500 millimeters and increase this one to be 2 meters like that. And now let's click on save and click start assembly to start creating the second spiral stair. Here's the parts of the second spiral stair will be assembled, the bottom rail and the top rail. And one more thing I would like to define it here for the radial cut to first post. That means here you have a mid rail and bottom rail. They will be for the first spiral stair. We need to select this one to make a cut for the mid rail and bottom rail. If let's with this image here, as you can see, this rail here, we need to remove this piece. Okay, so to remove this one and make the cut up to the first post, this option here, which is the radial cut to the first post, we need to check it before going to the to make it smooth at the start with the previous with the first post. Here we have the bracing of the spiral stairs. The final piece will be the pre-pads after importing the those clips. Okay, sorry, we forget to make the angle with a negative value. So here we make the value of the orientation of this one. We defined it as 45.5. So actually we need to define it as 360 negative 45.5. Okay, so it should be like that. So 360 negative 5, so it should be 314.5. Okay, so in that case, you will need to be care during data entry for the second levels and take the previous spiral stair in your consideration during the calculation of the orientation of the second spiral stair and the level of the second spiral stair based on the previous spiral stairs that you have. So for example, if we change the orientation of this one and click save, after updating this, inshallah, we will get this spiral stair on the correct level at the end of the previous spiral stair. Okay, let's run it, and during that we can make the open discussion. If you have any questions regarding the modeling of the storage tank. After that, inshallah, regarding the detailing, as mentioned on this session, we could discuss it at last session with the pressure vessel because it's the same basic, how to generate a general arrangement drawing, how to make a detail drawing, how to export the bill of material to your drawing, how to export the nozzle table, how to make another tables inside your drawing, importing pi tables, all of that. So any questions during the modification of this spiral stair?
Yes, thank you, Mr. Ahmed. We have few questions.
Yes.
I mean, not only related with spiral stairway, but also on bottom plate. Okay, just we will have a pause for 2 minutes. I think let the azan be finished, and then we will ask you.
Sure.
Thank you.
Now we have this. Yes.
Okay. Mr. Ahmed, related with the bottom plate, I have like a few queries.
Yes.
In bottom plate, as per API 650, we need to ensure that there should be the 3-lap joint. The distance between each 3-lap joint shall be 300 mm minimum. So is this check being? I mean, does it take care? I mean, the software does it take care automatically, or we need to check this manually?
If you would like to measure that you asking for, or
Yeah.
okay, as you can see, the overlap appears here with the 50 millimeters.
No.
Okay.
I'm talking about the distance between 3-lap to 3-lap. The same location. Can you go to the same location? If you zoom in, yeah, this is 3-lap joints, right? 2 3-lap joints. Okay, what's the distance between this plate?
You mean that one from that edge?
This one.
That edge?
Yes.
Yes, you can measure it. It's up to you. You can define it based on the width of the blade. It will not be automatically. It's based on the width of the blade that you defined here. For this blade, for example, you define this value as 1.5 meters. Okay, and based on this one, automatically you will get the value here.
Okay, so we need to check.
SEG will not inform you if it's make a clash or not. As mentioned here, you should make some visual inspection to check if you have clashes or not on the welding lines. Okay.
Another thing in API 650, it says that the width of the plate, there's length and width. So the smaller size shall be 1800 mm. The width of the plate shall be 1800 mm. Now, like when we are doing this, like nesting, I mean, not the nesting, but the arrangement of bottom plate, sometimes I was seeing that there were small plates coming up.
Yes.
So
the small plates, you can make a merge. If you have a small plate at the edge here, you can merge it, or it changes the arrangement of the row itself. For example, here, if you would like to make this one with, if this, let's take this.
Can we check the dimension of this?
Drawing, yes, we can do. Inshallah, if we open this piece.
No, just the small part. What's the dimension of that width?
Yes, for that part, for example, if you would like to measure the distance from this edge to this point, which is to the end, you have here 2 meters, 0.3, and the length of this line itself, the height is 1,100 around that. So that's the small piece here.
Okay. Okay, so we have to do this manually.
As a measurement, yes. After creating the arrangement, if you are worried about something, you could add it to a drawing and make some measurements to be sure that it's okay.
Yeah, actually, API 650 says that the minimum width shall be 1800. So we need to check this manually and adjust the bottom plate arrangement.
Yes.
Okay. Now, while you were making this arrangement of bottom plate, okay, because our one of the problems of bottom plate is the sump, because in big tanks there are a lot of sumps.
Yes.
So while you were making the arrangement of bottom plate in the SEG software, can we locate the sump in it so that we can arrange in SEG itself?
No, it's not an option. But if it's very important from your side, you can raise your request, and inshallah, our development team can develop something like that to suit your requirements.
Okay.
Inshallah, we have the ability to develop something like that, but it's not. We didn't plan for it. But if you will need it, kindly raise your request, and inshallah, our development team can upgrade this option.
Okay, we will.